Hello, this is Mr. Huff, and let's talk about the Hazen-Williams formula. So this is what we use to calculate the head loss due to friction. And right here it says feet, but what they mean is feet of water. And if you have the feet of water, you can convert that into PSI. But for our calculations for dynamic head, you need to understand your head loss due to friction and the static head value, which is the difference between the elevation of the source and the discharge. So something I want to point out that this is an empirical formula, which means that if you look at the dimensions of this formula, they will not cancel out to give you feet of water at the end. This is based on experimentation and graphs, and really when you see a formula like this that has all these strange exponents like the 1.85 and the 4.865 like these, then or 4.8655. So if you see those exponents, this is trying to do some curve fitting and linearization. So that's what we're doing here to get this head loss due to friction. So your units are very important. Length of pipe has to be in feet, and usually this will involve a conversion of miles into feet, and you'll also need to know the, let's go look at this little note here. For our length, you need to understand the length of the pipe, which is usually miles converted into feet, and then the equivalent length of the fittings. It's the total of these two. Usually the equivalent length of fittings is just a small portion of the length of the pipe, but it will make a difference. So it's important to understand both of those. Those go together to give you the length of pipe in your system. So you're expressing your fittings as an equivalent length of additional pipe. That's what we're doing there. You also need to know your flow rate of your water in gallons per minute. And then you need to understand the Hazen-Williams constant, and it's a table. We'll talk about that next. And then the diameter of the pipe used in your system, and this is in inches. We're not going to have a unit on the Hazen-Williams constant because it's just a number to make this formula work. Okay, so let's take a look at the constants. I want you to notice where that constant goes. It's in the denominator. So that means if you increase this, you decrease the head loss due to friction. So higher is better in terms of what we're seeing here. And if it's lower, that means it's going to result in a higher loss due to friction. So low is bad, high is good. Okay, so let's look at this table here. And we can see that there's a couple of different values here. So you see clean new pipe, and you also see typical design values. If you don't know which one to use, go with the typical design value. Clean new pipe is when the system is brand new and it's installed, and the interior of the pipe is in the best shape it will ever be. As the system ages, you'll see that like cast iron and steel, the interior of these will pit and become corroded, and that causes the number, remember this is a denominator, so that causes the number to drift from 130 to 100, which means you're increasing that head loss due to friction, because the smaller that number on the bottom, the worse it is, okay? So normally in your problems, it will specify if you're doing this for clean new pipe or the typical design value. And you can see the ranges on the right here, what you would see normally. It could be anywhere from 80 to 150, but for designing, you usually use the typical design value. Let's take a look at a problem. So in this problem, it might read something like this. You have so many miles of pipe, and you have so many different kinds of fittings, and you do all the math to find the total length of your pipe system plus the equivalent lengths of your fittings, and you find that it's 17,000 feet. I'm just using nice round numbers so it's easy to do the calculation. And then we look at the flow rate in this system, and it's going to be 100 gallons per minute, so we have that listed. We are looking at the design value for brass, so we go look that up, and we find that it is 130. So that's our design value for C.
And the diameter of the pipe in this system is 10 inches. Okay, so that's how we kind of go through there and do that. That's would be an example of our problem. What we're looking for is a head loss in feet. And when we say feet, we mean feet of water for head loss. It's not just like a length, right? And then we look at our equation, and it's the Hazen-Williams calculation for head loss due to friction. So we have this 10.44 times the length times the volume of water raised to the 1.85 power divided by the Hazen-Williams constant raised to the 1.85 power times the diameter of the pipe raised to the 4.8655 power. So we're just going to plug it in. Hopefully this is making sense so far. To do it all at once in your calculator, you would do this. So start with the parenthesis and then do your multiplication first. So you're going to have 10.44 times your 17,000, which is your length of pipe, raising the gallons per minute by 1.855. Then we're going to divide and start another set of parentheses here, forcing the order of operations. We have 130 for our Hazen-Williams constant raised to 1.855 times the diameter of the pipe raised to 4.8655. Okay, so when you plug all that into your calculator, and hit enter, you're going to get this number here, 1.488 feet of water. And that's a whole lot of calculation for a pretty small number, but this is how you find the head loss due to friction.